Suzanne, can I thank you once again for a very nice presentation. Our next contribution is from the University of Michigan on amination over molybdenum nitrides and carbides, and it's going to be given by Shyamal Bej.
Yep.
Yeah.
Thank you.
Well, thank you very much.
Ladies and gentlemen, this is the manager on duty. Our emergency response team is on the scene and is investigating the source of the alarm. Thank you.
Good morning. I am Shyamal Bej from Department of Chemical Engineering, University of Michigan. The topic of my presentation is ethanol amination over nitrides and carbides. And the co-authors of this work are Christopher Bennett, Michael Milon, who is sitting in the audience, and Professor Levi Thompson. Before going to the actual talk, I would like to give a very brief introduction about nitrides and carbides and the importance of ethanol amination and the objective of our work. The nitrides and carbides are basically a class of interstitial compounds of metal and non-metal. And the metals are generally transition metals like molybdenum, tungsten, titanium, and non-metal is carbon for the case of carbide, and it is nitrogen for the case of nitride. And these materials have a number of interesting and important properties, like they have properties very similar to platinum group metals. They can be made in very high surface areas, and they are very much resistant to sulfur and nitrogen poisoning. As explained earlier that because of these important properties, they are found to catalyze a number of reactions. And some of the reactions of industrial importance are:
Ladies and gentlemen, the fire department has instructed the hotel to reset the fire system, and there's no need for further action on your part. All operations and services have returned to normal. We regret any inconvenience.
So some of the reactions of commercial importance are hydrodenitrogenation and hydrodesulfurization of nitrogen and sulfur compounds present in petroleum fractions, dehydrogenation of alkanes like butane to butene and then butadiene, water gas shift reaction, then dehydration of alcohols, and reforming, which includes both dry and steam reforming of methane. Now, as explained by my previous speaker, there may be some charge transfer from metal to non-metal, and this may create some acidic and basic sites in these materials. In fact, we have carried out a very recent study with some probe reaction, and what it has shown that these materials possess both acid and basic site. And the probe reaction was the decomposition of 2-propanol, and we have found that it gives acetone, which is basically catalyzed by...
Ladies and gentlemen, the fire department has instructed the hotel to reset the fire system, and there's no need for further action on your part. All operations and services have returned to normal. We regret any inconvenience.
And what we have found that these materials possess basic sites, and it can catalyze the decomposition of isopropanol to acetone, which is basically catalyzed by basic sites, and as well as it can form propylene, which is basically catalyzed by acid sites. And if that is the case, then the presence of acid, base, and properties which are very similar to noble metals can make these materials as a very noble multifunctional catalyst. And in fact, there are only very few materials which can have all these 3 properties together. And in this presentation, we will show that these materials can work as a multifunctional catalyst for an industrially important reaction, that is the reductive amination of ethanol to ethylamine. Now, coming to the importance of ethylamine, the amines are very important intermediates for the manufacture of varieties of chemicals like polymers, agrochemicals, dyes, and pharmaceuticals. Now, this can be made from the reaction of ethanol and ammonia. When they react together, they form ethylamine, and this ethylamine can undergo further reaction with another molecule of ethanol for diethylamine, which can further react with ethanol for triethylamine. And interestingly, the end members of this series, that is diethylamine and triethylamine, are much more valuable than ethylamine and definitely from ethanol. There are basically two routes for the synthesis of amines. First one is the reductive amination of alcohol, in which alcohol or aldehyde can be the starting material. If alcohol is the starting material, it undergoes dehydrogenation to form aldehyde, which then reacts with ammonia along with simultaneous elimination of one molecule of water to form an unsaturated amine, which is known as imine, which then undergo hydrogenation to form amine. And as you see that there are a number of activities involved in this, like dehydration and hydrogenation. So we should expect that one multifunctional catalyst is generally used for this reaction, and the catalysts are oxides of copper and nickel supported on alumina. This is the main route used commercially for the production of amines. Another route, though it is not very common, but still one process is used in BASF for the manufacture of tertiary butylamine from the reaction of isobutene with ammonia. This is the direct addition of ammonia with olefin. And here catalyst is basically zeolite type catalysts are used. Now based on this background, we have decided our work in three folds to see the catalytic activities of a couple of nitrides and carbides for the ethanol amination reaction. And the materials what we have selected are molybdenum nitride, vanadium nitride, tungsten nitride, niobium nitride, titanium nitride, and molycarbide. And then compare the results with some supported metal catalyst. We have used two catalysts, 5% platinum and carbon and 10% nickel and silica. And this material is quite similar to the benchmark commercial catalyst, 10% nickel and silica. And then we have established the pathways for this reaction, that is ethanol amination over one nitride, molybdenum nitride, for this reaction. And what we expect that the mechanism will be almost similar for the other nitrides also. Now coming to the preparation of catalyst, the carbides and nitrides are basically prepared by pseudomorphic reactions. Generally, oxide is the precursor, and the oxide is heated in a temperature programmed way, either in presence of ammonia for making nitride or in presence of mixture of methane or hydrogen to make carbide. And we see increase in surface area here. These nitrides and carbides are pyrophoric in nature and undergo very quick oxidation exposed to air. Therefore, to prevent that bulk oxidation, generally a layer of passivation is formed outside the nitride, which basically may be either oxynitride, oxycarbide, or maybe oxides. And this is done by getting a controlled oxidation at room temperature using 1% oxygen and helium. And when this material is again intended to test for any catalytic activity or for any characterization, the passivation layer is removed by carrying out a reduction using hydrogen at high temperature in the range of 400 to 480. The exact temperature for the TPR, for the reduction is determined through a TPR study. Besides this, we have also carried out some studies where we have synthesized the material and tested its catalytic activity without intermediate passivation. And what we have established that for at least nitride, that there is no difference whether we follow this route or in solution phase reaction. Now coming to the temperature programming for the synthesis, we generally quickly increase the temperature from room temperature to 300 centigrade within 15 to 20 minutes, and then slowly increase to soap temperature, which basically depends on the material we prepared. It can vary from 550 to about 1100, and we keep it for there about 1 or 2 hours, and then quickly quench the material to room temperature and then carry out passivation. This is general profile, but the exact profile for each material was determined by carrying out the EGS studies for each oxide to nitride or carbide conversion. Now coming to the implementation of this scale in the laboratory, we have taken a quartz reactor in which we have put the oxide powder, which is basically the precursor. Then we have used either a mixture of methane or hydrogen or ammonia for making either carbide or nitride, and then quenched it and carried out the passivation. Now, coming to the setup for the catalytic performance test. This is a conventional one using a microreactor. As I have mentioned earlier, that before measuring the activity of the catalyst, the material is reduced in the reactor using hydrogen at 480 to 500 Celsius. And the experimental setup, hydrogen was the carrier gas. It was passed through a saturator containing ethanol at 0 degree centigrade, and then it was mixed with another stream of ammonia. The composition of the stream before entering the catalyst bed was about 1% ethanol, 25% ammonia, and balanced hydrogen. And mostly all the data were generated were under differential conditions. So coming to the key properties of the materials, carbides and supported catalyst. The 5% platinum carbon have very high surface area, about 1200 meters per gram. Then 10% nickel or silica. Carbides and nitrides, they have also surface area close to 100. Tungsten nitride 68, then molycarbide 63, molybdenite 21, titanium 32, and niobium nitride about 33. Then coming to the CO-optic values, this is basically micromole per gram. Molycarbide of 55, molybdenite 42, titanium nitride very low, and 9.3. Then vanadium nitride 20, niobium nitride 14, tungsten nitride 57, and these materials have also lower values 13 and 29. Now coming to the results of the activity tests, first we will discuss the unsteady state behavior of these materials. This is a deactivation plot for molybdenite at a temperature of 200 degrees Celsius and a conversion level less than 1%. What if this x-axis is, y-axis is for the reaction rate, and this is for the selectivity of either ethene or ethylamine, and this is the timer stream. So what we find that within first 2 to 3 hours, there is a sudden drop in activity, and beyond that period, the rate of deactivation is much slower as compared to the initial rate of deactivation. And another thing, which is not very significant, but is that there is increase in selectivity in ethylene formation, and there is decrease in selectivity for ethylamine formation with time. If we compare the results with the commercial catalyst, that is 10% nickel on silica, the behavior is quite similar. Here also, we find that there is sudden drop in activity within the first 2 to 3 hours, and after that, the rate of deactivation is much slower as compared to the initial period. Here, obviously, there is no change in the selectivity with time, either for ethylene or ethylamine. Now, we have modeled this data for a deactivation model, Parlow model, and what we find is that the order of deactivation for molybdenite is higher, 1.1, as compared to for the nickels on silica, which is about 0.41, which indicates that molybdenite is more susceptible to deactivation as compared to the 10% nickel on silica. However, the activity, and as you'll see later on, the selectivity also, selectivity for ethylamine is much higher for molybdenite as compared to 10% nickel or silica. Now, we did the exerted studies of the deactivated catalyst after use, and we didn't find any change in the phase composition of the used material, that is the deactivated material. And we have carried out the surface area study also, and there was a negligible decrease in the drop in the surface area of the used material. So what we think that the initial rapid deactivation may be due to the blockage of the active sites by the product amines, which are much more basic than ammonia. Or the deactivation may also be due to the incorporation of oxygen into the nitride or carbide. If oxygen is incorporated into nitride or carbide, they will form oxycarbide or oxynitride, which are more acidic in nature. And because of the more acidity, this will favor the formation of ethylene, which is basically acid catalyzed reaction. So maybe because of that, we find increasing trend of ethylene selectivity with time for the case of nitride and carbide. Now, coming to the steady state behavior of these materials, these are the turnover frequencies for the formation of amine for various catalysts. What we find that 5% platinum carbon has a very high turnover frequency. However, some of our materials, molycarbide and nitride, they are turnover frequency is definitely much higher as compared to the 10% nickel on silica, and this is considered a typical benchmark commercial catalyst. And molycarbide is definitely higher, followed by vanadium nitride and molybdenite, and some of the nitrides have lower values as compared to 10% nickel on silica. These are tungsten nitride, titanium nitride, and niobium nitride. If we see the Arrhenius plot of this, Arrhenius plot of the amine formation rate for these materials, the traits are almost similar. Here again, the 5% platinum carbon has a very high rate throughout the entire range of temperature, which basically spans from 180 degrees Celsius to 210. Then followed by molycarbide, and then vanadium nitride, and then nickel 10% nickel on silica. And another thing which is important here is that the trend in the change of the rate of this turnover frequency for all these materials are almost same. We have tried to find out the activation energy for this plot, and what it shows that the activation energies are though not exactly similar but are very close. The molycarbide has about 24 plus minus 1. For all these things, the error is almost in the same range, plus minus 1 to 2. Titanium nitride is 17, vanadium nitride is 20, niobium nitride 21, molybdenite 26, tungsten nitride 30, 5% platinum carbon 12, and nickel 10% nickel on silica 60. So what does it indicate? That possibly the mechanism which is followed over 10% nickel on silica, it may be almost same what is happening over these carbides and nitrides. Now coming to the selectivity plots, this is the selectivity for all these materials for a very low conversion, less than 1% conversion, and here we find that molycarbide has very high selectivity for ethylamine, and it is even better than 5% platinum on carbon, and slightly better than 10% nickel on silica. And other materials are slightly lower, like molybdenite, niobium nitride, like this. And the selectivity for ethylene is very low for molycarbide, and this is a very good indication because ethylene is a byproduct for the reaction. And other materials have higher selectivity for ethylene, like titanium nitride, vanadium nitride. They have very high selectivity for niobium for this ethylene formation as compared to the commercial catalyst 10% nickel or silica. Now this is the situation if the conversion is very low, where we do not find any higher homologues of this series, that is diethyl or triethylamine. But if we keep the conversion higher in the range of 15%, then we find that there is some difference between the two materials, molybdenite and 10% nickel on silica. Interestingly, the ethylene selectivity for molybdenite is very low. Here it is very high as compared to the molybdenite. Then for ethylamine, 10% nickel on silica is very high selectivity as compared to molybdenite. But for molybdenite, the selectivity for the more valuable amine, that is diethylamine, is much higher as compared to 10% nickel on silica. And there is no triethylamine formation for 10% nickel on silica, but we get some triethylamine for molybdenite. And if we see the selectivity for only amines, it is almost similar. We just basically exclude the ethylene. Now, after establishing that these materials are good for the synthesis of amines from ethanol, we tried to elucidate the reaction mechanism for this reaction over nitrides and carbides. And we have found two intermediates during our earlier studies, which basically acetaldehyde and ethylene. Ethylene, little bit good quantity, but very, very negligible amount of acetaldehyde. But the detection of these two intermediates at least indicates that there may be two possible pathways for this reaction. Acetaldehyde can be intermediate for the reductive amination, that is, it can undergo dehydrogenation to form acetaldehyde, which then reacts with ammonia and eliminates one molecule of water to form the unsaturated amine, that is ethylamine, and then undergo hydrogenation to form ethylamine. Or it can undergo dehydration to form ethylene, and this ethylene can undergo direct amination with ammonia to form ethylamine. But at this stage, you do not know which one is prevailing over the nitride, or both are going on over the nitride catalyst. So to clarify that, we need to have some more information. And for that purpose, we need to know what happens in absence of ammonia. And can ethylene react to form ethylamine? Can ethylene undergo hydration to form ethanol or acetaldehyde. Reactivity of acetaldehyde, we do not have any information. And then can the product ethylamine can undergo decomposition to form ethylene. And to get the information about these queries, we have carried out a series of experiments which have led to some conclusion. And the experiments what we have carried out, the first one was the reactivity of ethanol with or without ammonia. When we carry out the reaction using 1% ethanol and about 99% hydrogen over molybdenum, we found there is no ethylamine, which is expected because there is no ammonia, but there is a very high selectivity of acetaldehyde, about 70% selectivity, and 30% selectivity of ethylene. But when we add ammonia, there is no acetaldehyde, trace amount of acetaldehyde, and which is logical because the acetaldehyde is reacting with ammonia to form amines. But interestingly, the selectivity for ethylene also drops from 30% to 5%. So there may be possible two reasons for this drop in selectivity. Maybe this ethylene is also reacting with ammonia to form ethylamine, or the use of ammonia may be blocking some acidic sites, which is preventing the dehydration reaction, which is basically an acid catalyzed reaction. So to confirm that, we have carried out some more experiments. We have seen we have tested the activity of ethylene over molybdenum, and when we use 1% ethylene, 25% ammonia and balanced hydrogen over molybdenum, there is no reaction and no ethylamine is formed. Similarly, there was doubt that the ethylene can also undergo ethanol and it can form acetaldehyde. To confirm that, we have used a mixture of 1% ethylene and 1.5% water and the balanced hydrogen, and there was no acetaldehyde formation, no ethanol formation. So which indicates that though ethylene can be formed over nitride, but it does not undergo any further reaction over molybdenum under the present states of condition. Now coming to the decomposition of ethylamine over molybdenum, we have used a 2% mixture of ethylamine and the balanced hydrogen. We have passed that mixture on molybdenum, and there was no reaction and no ethylene was found. So we can say this ethylamine is quite stable over the molybdenum catalyst.
We've got 5.
Yeah, I'll almost complete. Okay. Then to find out the reactivity of the major intermediate, the acetaldehyde, this is quite interesting. When we pass acetaldehyde with hydrogen, at the present state of condition there is no reaction. But if we decrease the flow rate, that is increase the space time, and increase the temperature a little bit, we found protonaldehyde, which is basically self-condensation of acetaldehyde, and which gives another indication that these have either acid sites or basic sites, because the condensation is catalyzed by either basic or acid sites. Then when we use a mixture of acetaldehyde, hydrogen and ammonia, we get ethylamines, diethyl, triethyl in the selectivity what I have mentioned earlier. But if I use acetaldehyde, ammonia, no hydrogen, I find the unsaturated amine, which is basically ethylamine. So with this information, probably now we can say something about the mechanism of this reaction over nitride. So it also follows a reductive amination, where ethylene to acetaldehyde is a very slow reaction, and then undergoes very fast addition with ammonia to form an unsaturated amine, which is basically ethylamine, and then which go first hydrogenation to form ethylamine. And ethylene can also form from ethanol over acidic sites, and this is basically a function of the ammonia concentration. If there is a large excess of ammonia, then the formation of ethylene is suppressed. So now coming to the conclusion, we can say probably we have demonstrated that nitrides and carbides are basically good amination catalysts, which can be compared with the benchmark commercial catalyst. Selectivity for diethyl and triethylamine are higher over molybdenum as compared to metal supported catalyst, and the mechanism which follows over molybdenum is perhaps a reductive amination pathway. And coming to the acknowledgement, I would like to acknowledge our graduate students, Jamie Pat, Chang Kim, Andy Taylor, and Camilla Turner. Thank you for your presence.
Very good. Very nice work. Very interesting. We've got time for some questions. Yes.
Yeah. It's a nice idea to use these types of catalysts for amination reactions. So thank you for this talk. But I have one question, I have one problem with your side product. So you have actually two pathways to build the side products. This is the elimination of water to form ethylene, or the decarbonylation to form CO and methane. But in both ways, I would expect that you to make a hydrogenation of both, so to ethane or to methane. So I never would look for ethylene as a side product. So did you ever look at methane or ethane?
We didn't get actually methane or ethane, but we have carried out some other reaction also, like decomposition of 2-propanol. We have found propane in those reactions, and it is reported earlier also that we pass like octanol. It is processed, but this work octanol we find 1-octene.
No.
Yes, I remember 10 years ago, more than that, 20 years ago, something like that. Alex Bej published the same reaction in GCAT, but he did not have such a fast deactivation in the catalyst from nitride.
Yeah, those are maybe probably the products diethylamine or diethylamine, which are more acidic and more basic in nature than the parent reactant, that is ammonia ethanol. So probably they are blocking some of the reaction sites. That's why till the product concentration is built up, we find the drop in activity for initial couple of hours. After that, it is more or less steady. Probably that is on our case. We are still getting out, identify the.
Have you explored different conditions of partial pressure and all that?
We are presently carrying out. We have not done that. Now we are carrying out.
But I think you have a much stable catalyst.
Yes.
Yes.
You made a lot of interesting combinations of reactants, but a missing combination, ethylene and ammonia. Did you try that? Direct elimination of ethylene by ammonia?
Yeah, we tried.
I mean, without water or hydrogen in it?
Yeah, without any ethanol. So we do not find
ethylene and ammonia.
Ethylene and ammonia, yeah.
Without hydrogen and water in it. Did you try that?
Without hydrogen?
Without hydrogen or water?
Yeah, we tried, but the drop in activity was very fast. Probably ethylene is undergoing some polymerization, something like that. Very within 2 hours, it almost became zero. So we couldn't take any significant reliable data. Yeah.
One more? Okay, thank you very much.